Hi guys, how's it going? Today we're gonna be talking about some updates that have been happening within Inference compiler, some news, because I make videos not very frequent, so there are quite a bunch of things to talk about. And actually, my agenda for today is I will share some thoughts about Inference compiler design and how I see strategic progress in its development, some new CLI entry points that I have implemented, related functionality to Wasm code generation, tests, and all these things. So they're not going to be super detailed as the previous one, but it's more like on a high level. However, I think these things and bits that I'm going to be talking about are really important, especially if you or like I am approaching such a huge project as a compiler development. So let's get started. And the third thing is I want to talk about is the design principles I have been recently thinking about and made a post on X and in Discord, everywhere on Reddit. So try to scatter information about Inference and the progress I've been making to get as broader audience as possible. So for Inference compiler, I really want to make it flexible, well maintainable, so people can really contribute into it. Because other compilers, they're usually huge, very difficult to understand the code base, and so there are many reasons why it's hard to start contributing to compilers. I want to make it be not like that for Inference. And the idea I like, actually, is one I think that was initially introduced by Chaz Kim. I might wrong, but about the origin of the idea. But the thing is that if you think about the compiler as a three huge phases structure, which are like the first is a front end, which is parser. Then the middle part is intermediate representation with all like static checks, and the latter part is a backend with the code emission. So what the nanopath for compiler design assumes. So if once you are ready with the front end parser and you have an abstract syntax tree and you emit or produce the first intermediate representation, of course AST or typed AST are some kind of intermediate representations themselves, but let's say you have like a language intermediate representation that you produce based on the user's input from AST. So then you can add as many granular transformations from IR to IR prime within the cycle of transforming user input to the bytecode ready generating structures, intermediate representation. It means that after creating every new version of the intermediate representation, you can perform certain transformations like monomorphization or other optimizations, and then you actually produce like another formal language, another intermediate representation that you can actually prepare certain checks very specific for this IR and analyze it, and then the next step, like subsequent steps, they perform like new rounds of analysis and emit new formal languages up to the latter, which will be used for bytecode generation. And it's really great, I think, by various reasons. One is having formalized languages in between and enabling those many standalone and not related analysis phases. They can really enable very powerful framework for semantic analysis and optimizations. However, the obvious trade-off is performance, But I think, even what we have with Rust, so we can live with it, and it's not the big deal, this performance trade-off these days. So I think it's more or less manageable, especially with, some engineering hacks. However, this approach I don't think is really good for inference, and the reason is inference is a formal specification language, is designed to be as much transparent and literal as possible, meaning the source code or the specification code should be very similar and resemble the code we emit at the very end. So a developer can really read the source code and compare it and match with the emitted bytecode, or like textual representation of the bytecode. So we cannot do all these transformations because it will obfuscate the end result. Therefore, it will be difficult to find, possible mistakes or contradictions, or like some semantic or other shifts in the end result. And the second thing, which is very related to this one, is optimizations. So since inference is not supposed to be like a super, or even not super, like even to be a compiler to produce a code to be executed directly, hence it does not aim to emit like very optimal, efficient code. The goal of inference is to emit as closer code to the source one as possible, because we want to achieve outstanding robustness and clarity in proofs that we do. Optimizations here are not important at all. So these two things that NanoPath, I think, really shines are not the case for us. So as a design, we're not gonna use this framework or approach. But what I like is the module structure. So I think instead of producing intermediate representations internally, versioning them or like one after another, passes, they will not mutate the structures that augment the final result. Instead, I foresee having multiple passes that will, individually, maybe even in parallel, analyze code and then return a meaningful results to a developer. Another important thing here is custom Wasm emission and Codegen that I have been recently approached. So why don't we use LLVM or MLIR or other intermediate representations? So the reason is we really need to have super reliable and reproducible bitwise identical builds from build to build. So any given input must produce identical output, identical bytecode on any machine, regardless anything. And we can achieve this only if and only if we control code generation ourselves. So that's why we are using and will be developing custom Wasm emission ourselves and Codegen. So that's really exciting. Another strategic thing which is really important, in my opinion, is how to develop a compiler from the kind of project management perspective, like feature planning, etc. So as one friend of mine shared with me a paper, which I think also from the check scheme space, And in their educational purpose, they say that it's the quote, right? The development of the compiler must proceed in small steps where every step can be implemented and tested in one sitting. The result of completing every step is a fully working compiler. The compiler writer therefore achieves progress in every step in the development. I think many things here are very well framed, like psychological and technical, because if you can observe your progress and you see how compiler evolves, you really get satisfied with it. So for Inference, I also want to apply this vision for feature development. So I foresee roughly the following steps to achieve. One is base module and function generated as a base functionality, which is required to formulate a minimal Wasm unit, which is a module. Two, I32 literals returned from a trivial function, which is already actually achieved. Here is the short demo video. Then immediate constants like a boolean that are stored as I32 are manageable. Then we introduce local variables, function calls with one argument, binary expression operations except assignment and conditionals. By the way, about Codegen and assigned conditionals and loops, there is quite an interesting material I have been observing, so I probably will tell more about that later on. Conditionals, then assignment are being set in the plan. Then memory allocations with arrays, structs, full function call support, finalized syntax coverage. Then we bring aliases and libraries. Finally, external functions, and the very end is error checking, which I think should be, instead of be a final step, more be like for every functionality and a milestone or like a smaller version, it should be covered as like with unit tests and like all possible tests, like error checking and handling should be smeared, right, amongst, but maybe here it's better to say like the latter, like 14th point is about static analysis of the source code, something like that. All right, and now let's take a look at some screenshots from the code and updates. There are not going to be many, but I think they're really worth showing and observing. Yeah, and by the way, the repository and the source codes are going to be open in January 2026. So if you want to contribute, you're really welcome. I will be really happy to see external contributions, discussions, opinions. So join our Discord and all our social media and cast your opinion. So feel free. I updated command line interface for Inference compiler, and actually I adopted the idea for the CLI for testing purposes from the Write and See compiler book, which is really interesting actually to read, so I highly recommend. So now we have in our interface is it used to be a path to the file that we gonna compile, and then we have various flags. One is parse. This actually is for testing only the front end part, which like parsing is source code. Then analyze part, which assumes to do like static analysis, and Codegen flag says and like navigates a compiler to emit Wasm bytecode. If -o flag is set, then we emit. So we save the file as an output. So and -v generates a v output. So actually the idea here is that you can really quickly assess if everything works still. So you don't need to read files, and you don't need to actually like go everything one by one. If you're like working on particularly on analyzer, like every time execute Codegen is not really necessary. So this like allows you, it gives you some sort of flexibility in what to execute, what not to execute, and this work with artifacts is also can be helpful and beneficial. So I really adopted it and enjoying being it as it is so far. How it was implemented, super easy. Actually, at the very beginning, I read all command line arguments. Then I just go one by one. If I see, if a user says that we need a Codegen or any lower domain flags, then we do, like generate AST. I remind that I use a Tricitor as a parser right now. Then in case of analysis or Codegen, I do a static code analysis. It's really just this function does nothing. It returns AST as it is, but it assumes to return some list of errors, warnings, and like diagnostic, broadly speaking. And the Codegen generates from AST a bytecode, as you can see here. And then if we need to save an artifact, we do so. In case of a V output is requested, it also does the same. So this is actually the, I can say like the state of the art, but it sounds a little bit too strong. So this is like a minimum code that we can compile and actually emit a bytecode and run, execute right away. And this is the textual output of the same code. So it's super easy. It's just a constant for 2 that we return. And yeah, it really works. How Codegen is organized on the high level. We receive as an input a typed IST, which is an IST, and for every expression we have a type information about, as well as arena having all supplement information about nodes, and all nodes are actually sitting in arena. Simply optimize memory usage to eliminate unnecessary fragmentation and all these things. So of course, if AST has no source files or more than one, which were not supported yet, we just return. Otherwise, we actually build a function. And how we do it? Of course, we first need to create a structure for a Wasm module, which contains of these minimum required sections to add and create a function, which are module, types. Types are actually the information about types, which are functions, like functional types. It's more about like signatures, let's say like that, right? We'll see what exactly it looks like a little bit later. Functions, a table of functions and indexes. So we know where, like at what offset or like what index we can use to access, to call a function. Exports to being able to call these functions outside of the module. Calls are actually function bodies. And the next type index, we need to properly index or address types that we push to the module. This is the example of a unit test I have. I really took it from so this is actually an example taken from the Wasm encoder documentation, because I use Wasm encoder for encoding and emitting Wasm. what do we do here? We create a module, and for a type, we need to have information about what type it is. In case of a function, function type is actually defined as a input and output. So it's like a parenthesis with parameters, right error result. That's why we need to specify those. And then we need to set an index for a function, as I said, to be able to address it. And then we export it with a certain name. In this case, it's a hello world. And then we encode a function body as follows with construction set. We can use like this chunk approach or add bytecodes one by one, as I do in the actual function body Codegen. And then we just finish, and that's pretty much it. So it's pretty easy. So what's happening now? Of course, the code is very... So I actually covered the only one case to let the compiler to the state of being able to generate as a very minimum code and very minimal function. So here it is. So we create, once we push a function, we take the next type index, then we increment it, push a new index, and immediately like export the function here. Then we read parameters. As of now, I do not support parameterized functions, and that's why it's just an empty array. Then we collect a return type. In my case, I support only those primitive types. These are string literals, which I will substitute as like some enums for better robustness, similar to this one, to be able to distinguish, without an ambiguity in case and all these things. Yeah, so using actually strings for such things is not really pleasant. Then what we do, we add a new function as a type to the types section, and then there is now inline, but it's going to be like a separated logic for handling statements and expressions, which we need to encode as a function body. As we saw on the previous slide, there are two ways to encode functions. Like we can chunk instruction to instruction, or we can push them as instructions, like function, instruction, and then the instruction we need, etc. Like on this line or here. And then as function itself by nature is a body, or like, the function's body or block of statements, we push it to the code section, and then we're able to generate and run Wasm. For some, infrastructural level, I added a couple of helper functions to the test section. I want to make a structure, and I think I made it, to play a bit more to figure out if there are some caveats, but seems work fine. So I want to mirror in a tests directory, test with the other project structure. Per se, if it's a module of Codegen or AST, I should have the same structures in my test directory, like test/src/ast or Codegen, and then the same file names as I use in crates should be used in the tests. So I can I mirror actually the structure of modules I test. And I think it can be very helpful. And the same for Codegen. If we test Codegen, then we need to be able to, take either text input or small tests written in Inference that we compile. If we want to test like from CLI or in this case. So what this function do? So I can take a test file, analyze the current test location in the test directory, and then take this similar with the directory where code examples are stored. Similarly, I can do it for Wasm inputs. So I can say like, okay, take this file with Inference and back to have this Wasm as output, and then I can assert literally. How to do it? It's pretty easy. I just take a module path, and then split them to the standard module separator, and then collect all together. The assertion I do for Wasm emitted bytecode is I first match length, should match, and then I actually do this assert length. Assert equals to two vectors, or here it's like a reference to slices, and then like yet another. Maybe it's like exceeding, but I would really like to do it for diagnostics. It's actually good, also in case. Yeah, I'm thinking about like maybe we need to swap or flip this too, or this actually is redundant, right? Yes. Maybe if a module is bigger than, so it can be a little bit more performant. Okay, long story short, I then compare like byte by byte, and I assume it can give me really good diagnostics. So the trivial test looks as follows for a Codegen. So I have a test name, which is trivial. Then I get the source file, source code, then expected with these helper functions, and super easy. Read all these expected bytes and assert WasmModules equivalence. It's pretty easy. Like this infrastructure gives like enable. I think actually this can be wrapped with some macro. So what the write-in unit test for Codegen gonna look like? You need to write inference, compile it manually. If everything works perfectly, you just like add a macro with the name of the test and file like input and expected output, and it's gonna work automatically. Yeah, I think it's a good idea to implement actually. Yeah, and as I said, so this is the module, the base test where the trivial test is. So it refers automatically to, as I said, to the mirrored path, Codegen Wasm base, and it takes from this file like this trivial and trivial Wasm. So if I add like non-trivial test into the base RS in the module, I just add non-base inf and non-trivial inf and non-trivial Wasm here, and it will work automatically. Yeah. So this the ease of writing unit tests is really important, because like test-driven development is a very big thing we need. And also like small updates about Plant. I really enjoy how Rust Analyzer team implemented it, and I think it's very sophisticated, very clever, and reasonable to be considered as a reference example of code analysis. And I really like those, really Rust top professionals who are up to this project. So I want to adopt as many techniques that make sense to take from the Rust Analyzer and implement it in the Inference compiler. Yeah, I think this is for the formal part. That's it. Okay, guys, thanks for watching, and I hope you enjoy this kind of video. Not super low level into implementations, more like a high level and project-wise level. I actually plan to maybe record a video once a month with updates I've been doing so far, and what are new features, challenges I'm facing with, what problems I'm solving, and more like, show work in progress instead of like some educational content, lecture like wise. So stay tuned, and yeah, if you have any opinion or ideas, share. Please subscribe, by the way, on the GitHub as usual. Here also might be useful if you want to see on updates. Yeah, thanks for watching, and cheers. See you.